Okay, geology class, here we go with video lecture number 1 on metamorphic rocks. I'm trying to use the split screen with a little window of me down in the corner here. I'm not sure how this appears to you, but we're going to give this a try. So today the topic, as I mentioned, is metamorphic rocks, and if you've got your notes handy, you can see that basically the first line we're talking about two main forces, and actually a third force that's also involved with changing a rock. Like I've got this piece of granite here. What could change this rock? Certainly heat is one of those forces. Pressure is one of those forces. But then also a less known one, chemical action is a force that can change a rock like this granite into a different type of a rock. Now, it's important to note, though, that we can't be creating conditions that cause this piece of granite or this piece of basalt to melt and then reform, because if that were the case, we would simply have a new igneous rock. It would not be a metamorphic rock. The analogy could also be made between what you see in the picture here. This gentleman is just throwing this fine pot. He's putting handles on it. I've seen our ceramics people here at Bethel work on these, and it's just amazing to see the skill, the talent that those people have. I'm envious. And wouldn't it be a shame if this person, after having created this wonderful work of art, puts it in the kiln and then it just melts into a puddle? You know, that's not what we want to see happen. So there's a change that occurs in this pot. There's a change that occurs in this granite or this basalt in the solid state to turn them into another type of a rock called a metamorphic rock. And that's what we're going to look at today. I initially had a map of, I had Google Earth up because I wanted to make the case that Minnesota has a number of very important landmarks that have to do with metamorphic rocks. So we'll go back there. And I'm looking down here in south western Minnesota at the town of Pipestone. There's actually a county down there called Pipestone. Now I have a number of my props scattered around my desk here, so I'll be moving around to grab them from time to time. This is a kind of rock. This is actually pipestone. And this is a metamorphosed claystone. Now, claystone would be the metamorphic parent of this rock. Claystone, if you remember, has clay-sized sediment, but it would not have layers, so we would call it a claystone. If it had layers, it would be a clay shale, like this one here that you saw, and we'd call it a shale. So this was made from a parent rock called a claystone. And it was metamorphosed into this rock, which is pipestone. It's also named Caitlinite after the photographer George Catlin. I think it may have been a painter. I'm not sure. There's an artist, George Catlin. Caitlinite, anyway. And this metamorphic rock is very workable. The tribes in the area, I assume it's Sioux, Dakota, Lakota, not sure which, were able to work this into the pipes that they used in their ceremonies. And that's where the name of the county and the town come from, Pipestone. It's after this particular metamorphic rock. So it has significance in a lot of places in Minnesota, and that's just one example of them. So it's important to also note that you never get conditions where two parent rocks, like for instance this granite and this basalt, would be forced together with such heat and such pressure that they would actually fuse. If the conditions were that extreme, we would have igneous rocks and not metamorphic rocks. But you can take one parent rock like this granite and subject it to metamorphic conditions and get multiple daughter rocks from this one parent rock, multiple metamorphic rocks from this one parent rock. Now in lab, if you remember, we characterized the formation of sedimentary rocks based on the conditions that formed them. We had low-grade metamorphic rocks, and those were metamorphic rocks that formed when the parent rock was subjected to just a little heat and pressure. So for instance, you take this clay shale that I had up here before, and I don't know if you can hear this, but if you remember, I dropped it on the counter, and it had a sound. And then it's subjected to heat and pressure. It undergoes changes and produces this metamorphic rock slate, and I'll drop it. And the idea was the parent rock, shale, drop it again, is not as dense because it has not been subjected to pressure. And the daughter rock, slate, is much more compacted, much denser. And so when I drop it right now, I don't know if that comes through on the recording, but it's a higher pitched, ringier sound, indicating that it has been metamorphosed. It has been subjected to pressure which has squished together, if you will, the minerals that make it up. Okay, so in your notes, we're looking at the intensity of metamorphism, and we talked about slate being a very low-grade metamorphic rock. Basically, it's very dull because the mineral crystals in it are very small. If you crank up the heat and pressure, the mineral crystals will grow a little bit larger, and you'll get a phyllite here. The surface is satiny, but you can't see individual sparkles, and that would make it a phyllite. Crank up the temperature and pressure more, and we'll have now individual cleavage planes visible. And this is a mica schist. You can just make out the notion of layers there. But the mineral crystals have grown because the metamorphic conditions are more extreme. And so we would then call this a schist, if you remember. Crank up the temperature and pressure even more from a schist, and you get alternating layers of light and dark minerals, like with this nice rock. Isn't this a nice rock? Yes, I think it's a very nice rock. But, you know, we, of course, never want to take it for granted. Anyway, nice, yes. Okay, and crank up the temperature and pressure the most. If you remember from lab, we would get migmatite, which has alternating layers of light and dark minerals. The light minerals have actually melted, but you'll notice most of this rock is that dark gray color, indicating it remains solid. So we still call this a metamorphic and not an igneous rock, even though part of it did melt. Most of it stayed solid. This is migmatite, indicating the highest grade metamorphic condition. Okay, so we know that there's changes that occur structurally, but I also want to make the case that, I can find what I did with it now. Somewhere around here I have that little, there it is, little piece of clay shale. If you look at this little piece of clay shale, I had a former student, I think I might have mentioned this, might not have, that, let me drop Google Earth off here. A former student that took this clay shale, which is common in this area. You find it all along the Mississippi River. And he purified it, put it in water, crushed it down really fine, got the impurities out, and he fired it in a kiln, and this is what came out the other side. Now, he did not glaze this or color them in any way, but there was simply a color transformation that occurred when he took this clay shale, got the clay out of it, and fired it into a brick. He also then took that clay and he made this mug out of it, and he used the clay for a glazing on it and made another look. Dude is talented, I'm telling you what. That's some good work. Okay, all out of this clay shale and subjecting it to metamorphic conditions that cause changes. Well, let's just take a couple minutes now then and look at those changes that that occur as we're talking about metamorphic rocks. Okay, so the first one is temperature. So temperature and the geothermal gradient. The idea that the farther down the earth you go, the hotter it gets. And to make this case, I'm going to bring up the example of the Home State Gold Mine. And so if we look at the Home State Gold Mine, I'm going to go back to here. This is what it originally looked like. Hopefully you can see this on the screen. Maybe I'll zoom in on it a little bit. Okay. Formed in 1876. It operated until 2002. And so when it was operating, this is what it looked like in the old days down, well, not real old, kind of old days, down in the shaft itself. A fairly hard rock. This is what they were after, veins of quartz with gold in them. Homestake was considered a fairly low-grade ore deposit. You didn't find a lot of gold this concentrated, but it was such a huge ore body that it was able to support that mine for over 100 years, 125 years. Nowadays, this is what it looks like from the top. This is about 1,000-foot deep hole, and if you look at it here, this is where it goes from the bottom of that hole. It goes another 7,000 feet into the ground. At the 4,500-foot level, the rock, the atmospheric conditions are about 90 degrees and about 100% humidity. It would be nasty to work down in there without ventilation. And down in the deepest parts of this hole, it is 8,000 feet deep, and we're looking at water that comes out there that's at 185 degrees. So the idea that it gets hotter the farther down you go is verified by this, what we just see going down in the Homestake Gold Mine. This mine is, of course, groundwater floods it, and it's being pumped out right now. And Stanford is going to continue to develop a deep underground research center in the Homestake mine. And it's kind of interesting how they call it Dussel or something, like deep underground something. Anyway, they're making use of it. But if they didn't pump the water out, this whole complex would fill with mine water, with groundwater that seeped into there. Now, I'm going to put a link on Moodle, and I want you to stop at this point and watch, about 7 minutes of a video, build it bigger. And in this video, they're looking at an even deeper mine. This is 8,000 feet. The mine they're going to look at is one in South Africa that goes down to 13,000 feet deep. And the conditions that you see at the bottom of that mine, I hope will reinforce this notion that the deeper you go, the hotter it gets. Okay, so take a moment, pause the video, and go look at that recording. Okay, well, hopefully you're back from having done that. And if you look at your notes, there's some points here. The geothermal gradient, the idea that, how much hotter it gets for every kilometer deeper in the ground you go is the geothermal gradient. There's some places on Earth where, it doesn't get a lot deeper the deeper you go. Let's see here. Yeah, right here. If you remember our famous Scottish gentleman, I'm not going to play the video here, but here we have, well, I'll play just a second of it. Okay, so you can see this is subduction going on, and right here underneath the ocean, so this crust is going to be very cold because it's deep ocean anyway, and it's subducting down, so this is already cold crust. So if you were to drill right here through all this crust right here, all of this crust is deep under the ocean. This that's subducting deeper is cold to begin with. So this would have a very low geothermal gradient. This rock would not get a lot hotter every kilometer in depth deeper you went. And so a low gradient, if you look in your notes, would be about 10 degrees Celsius increase for every kilometer deeper in the bedrock you go. That's a low gradient. But then we go to some other places on Earth where the opposite is true. And if we were in lecture right now, I would ask you some places where you thought it might get a lot hotter for every kilometer deeper in the ground you go. And I'm guessing somebody would have said Yellowstone, and you would be right, or near any magma chamber. And for an example, this is Morning Glory Pool, and it is in Yellowstone. So the water at the surface here is just about 157 degrees Fahrenheit. If you've been here, maybe you've seen some people walking around the edge of this, and I always remember little kids walking around it, and they were in harnesses. Their parents were so mortified that they would fall in the pool and become instantly boiled to death. Of course, that would happen if they fell in, but I don't know what the likelihood is. Anyway, that's obviously water that's very near a magma source. You dig down in the ground here at Yellowstone, and you're going to find a big bump in temperature. And so a high-grade piece of Earth's crust, like at Yellowstone, would see 40 degrees Celsius increase in temperature per kilometer in depth. And I would guess in the Yellowstone area, it would probably be more than that. Okay, so generally speaking, rock can take a lot of heat before it has to get out of the kitchen, before it changes. And so in your notes, it says 50 to 200 degrees Celsius is low-grade metamorphism. That means you take this piece of granite, and you subject it to 50 to 100, 200 degrees Celsius, it'll change a little. But you crank it up there to right close to melting, like the migmatite, 600 to 1200 degrees Celsius, and you're going to see a lot of metamorphic change, just shy of melting. Okay, so we're going to shift gears then. Let me look and make sure I haven't forgotten any of the sites that I wanted to bring up. Nope, looks good. So if we can shift gears then, now I would ask you as a class, where are places that rock would be subjected to a great deal of pressure, not temperature? Now, of course, when you increase the pressure, you also increase the temperature. That's just standard. But I'm guessing that after a little bit of an awkward pause, some of you might have had some really good ideas about that. And I just showed one. If I can get this one here, come on. Maybe it's not going to let me. There we go. If you look right here where you've got this plate colliding with this plate, boy, you know, if we back that up a little bit even, I mean, when they first impacted, where those two are colliding together, well, there would be a lot of pressure right there. Another place we could go, just downstream from Minnesota, right here in this region, the Mississippi Delta region. Okay, if you can think of all the sediment that this river carries out into the Gulf, all of this portion of the Gulf, because the Mississippi didn't always used to just flow here, this whole area is created as sediment was delivered to the Gulf area from interior of North America. There's layer after layer after layer after layer of sediment there. The deeper layers would be deeply buried and subjected to a lot of pressure. Okay. Now, in your notes, it's kind of interesting to me that geologists take great pains to differentiate between deformation and foliation. Deformation is basically taking a mineral, well, I don't have a mineral here, but you could think of this granite, and squishing it, flattening it. That would be deforming it. To rearrange the minerals in this rock into layers would be foliation. Now, they almost always occur at the same time, deformation and foliation. The minerals get flattened and they get pushed into bands. But geologists are very particular about differentiating those two, so there we go. So in your notes, it says pressure from deep burial, like the Gulf here, or from plate movement, leading edges of two colliding plates, good examples, cause deformation. Minerals in the rocks in those locations get flattened. What kind of pressures are we talking about? Well, they're so big we have to talk about them in terms of kilobars. Bars of barometric pressure are one thing, but kilobars. 1 kilobar is 1,000 times the pressure you're currently experiencing. You are currently ignoring about 15 pounds per square inch on your body surface over your whole body. That's the pressure that you are currently experiencing. That's pushing us down and holding us onto Earth's surface. Maybe it doesn't feel like there's 2.5 cartons of milk on each square inch of your body, but you've come to get used to that, and that's what it is. Of course, a rock can take a lot of pressure. Now, we dealt with pressure a little bit in the past when we were discussing ocean features, and well, all fingers. Oh, can't quite get this right. Ugh. Okay, this is the Trieste. This is a submersible that the two gentlemen, Picard and well, I forget what his name was, Don Walsh, went down to the bottom of the Marianas Trench, 35,000 feet beneath the ocean's surface. Now, they weren't in this. They were in this part right here. This was holding fluids, basically gasoline, that would allow them to float, and they would just basically pump the gas out to get them to sink. Kind of sort of a polluting sort of thing, but anyway, that's what they did. Okay, so there's the Trieste, and we talked about what would have happened if these little observation windows, it's kind of on the other side here, if that had cracked. Well, the pressure, 8,000 pounds per square inch. That's, what do we say? Maybe 2.5 minivans per square inch. If that window had popped, that pressure would have probably flattened this in an instant and everything in it. So that's the kind of pressures that humans can't take. But a rock can take a lot more. A rock can take 3 to 4,000 kilobars, or 3 to 4,000 times the pressure you're feeling, or 3 to 4 kilobars, before it begins to change a little. And up to 12 to 15 kilobars, and then it changes a lot. And above that, well, if we look here, we can see that the pressures get so high that the temperature also increases. So here's temperature increase this way, and here's depth. So increase in depth is analogous to increase in pressure. And this red line, you'll notice how it changes, because the deeper you get, you know, you're going to have a corresponding heat that comes with that. Okay, so in that process, foliation occurs. Now, I've got a really bad recording here, but I'm going to play it right now. And it's just an animation of this process of foliation. So let's see if I can get it to play. I don't know why I left my mic on, but okay, so here's a piece of granite. Here's it being metamorphosed. It's being basically deformed and foliated at the same time. And you can see, oops, I'm going to replay that. Maybe I'm going to replay that. Okay, again, here we've got granite, and it's being subjected to pressure, probably by the way it looks from above and below, so it's being squeezed along these lines. And we get the light and dark minerals sort of migrating to kind of bands or layers in there, and separating out to form the metamorphic rock gneiss like we see down here. So here's the igneous rock, granite or a diorite, and the metamorphic rock gneiss. That is the process of foliation. The notes say the parallel and subparallel arrangement. Subparallel means kind of parallel. Of flattened or platy minerals. The deformation process has flattened them. Platy minerals are like clays. That's a good example of what a platy mineral would look like. Let's see if I go back to here, and I think I can find quickly a clay mineral. Maybe I can. Maybe I went the wrong one. Clay micrograph, there we are. Okay, so here's clay minerals, very flattened, very platy, very dish-like. Remember, these little particles of clay here moving easily over one another is what makes clay feel slippery smooth. Okay, that's a clay mineral that's already flattened or platy, and that's what foliation arranges, if you will. Okay, a couple last notes. That other one, chemical action, if you remember from lab, I had you know skarn, okay? And this was skarn, the pyrite rock, skarn, okay? And skarn was the reason I had it in the rocks that I wanted you to be able to identify is because it's the example of a rock formed by chemical action and this process of metasomatism. And basically, when you look at this piece of skarn, what you want to think about, one way that it's formed, is hot seawater being sort of forced through a body of rock and metamorphosing it. Now, this is showing an example using basalt, but it could be a granite if it's a marine volcano that had, or Pluton that formed deep under the ocean and got forced through it. Anyway, anytime you get hot water going through a rock body, that hot water is going to dissolve some of the minerals, and then as it gets away from the heat, it's going to deposit those minerals and possibly create a vein deposit. We're going to show you some examples of those in the very last thing today. So anytime you get ions that come from outside the body of rock, that's what metasomatism means. Meta, above or beyond. Somatic refers to the body. Metasomatism is ions from outside the body of rock, could be a piece of granite, carried into the rock by hot water, be a good example, can create metamorphic rock like a skarn. Okay, then it talks about the last thing is that the three general types of metamorphic environments. There is contact metamorphism, and the best example of that would be a magma chamber like you see here. And the rock surrounding that magma chamber is going to be subjected to the heat from that magma chamber. The closer you get to that magma chamber, the hotter the rock. It's almost ready to melt. It might be a migmatite there. It probably won't be a migmatite because there's not enough pressure to layer it. It would be probably a non-foliated metamorphic rock. And examples of that would be like marble, okay? Or this marble. I had a former student get this for me. This came from Michelangelo's quarry. The same quarry that produced the stone that was made into the David. This rock came from it. Randy, I think Michelangelo did that one. Maybe I got to check. Maybe I got to retake my what is your art class now? It used to be creativity in the fine arts, whatever they call it now. Anyway, that's contact metamorphism. Change of the rock due to heat because it's so close to a magma chamber. Not much pressure. Temperature is almost solely what metamorphoses the rock. Another example of that could be quartzite. No layering, no foliations to this. Okay, the next one on your list is regional metamorphism. And that was, like we saw here in the video, this one of, nope, not that one. This one right here. So it may occur all along this trench and they have those high pressures, so it'd be a larger area. We call that regional metamorphism. As we showed at the bottom of, or in the Mississippi Delta region. And then lastly, there's hydrothermal metamorphism. This is caused by, as we said, the movement of hot water. And that hot water, it might be ocean water. It might be juvenile water. Remember, when we were looking at volcanoes, we were interested in what made them explosive. We talked about volatiles. The volatiles were either carbon dioxide or water. And so we know there is water in magma, and that can be a source of water for hydrothermal metamorphism. Metamorphic water, if you can squeeze rock so hard that you can actually squeeze the water out of it, and you would heat it in the process, which would just make the metamorphism, metasomatism more effective. And then lastly, I mentioned groundwater or ocean water. Last thing I just wanted to show you in this process of hydrothermal metamorphism. So you picture here, you've got the heat source. There's the magma. It's affecting these overlaying bodies of rock. So if we zoom in on this area right here, here's the heat source down here. That's the red arrows. It's moving water, metasomatic materials through this layer of rock. And as it does so, it's dissolving them. But as it continues to move them away, now this is seawater here, away from the heat source, they cool. And so they might cool in bands or layers. And then that seawater descends back down to do the same thing. So basically, this area is going to see dissolved minerals. As they cool, then they will get deposited. And those deposits can create what we call vein deposits, the mother lode, if you will. And just to show you what that looks like, here's an example, not unlike what we saw at the Home State Gold Mine. This is a quartz with gold in it. Here's another look at that same type of a deposit. And you can almost picture hot water moving away from the source, getting to here, cooling to the point where it could no longer keep the gold in it dissolved, so it deposited the gold in a vein. Maybe it moved a little farther and it deposited the silver in another vein. That Home State Gold Mine, they removed 43.7 million ounces of gold, but they also removed 9 million ounces of silver. So oftentimes these valuable minerals are found alongside one another. Here's what you might find in northern Michigan. This is a vein of copper, so formed the same way. Okay, folks, I kind of lost my clock here. I hope I haven't gone too long. That's what we've got for metamorphic rocks. This is the material that will be included in the exam on Thursday. And yeah, hopefully that's good. If you have questions, certainly feel free to email me or call me, and I'll try to do my best to answer them as quickly as I can. All right, thank you.